hello everyone. Nice to see so many people that came despite the monster that is the title of my talk. Oh, right. Yeah, so I'm going to break down this title because there are three words in this title that are important that I'm going to be focusing on this talk. The first one is triples. So I'm going to be talking about what are triples and why are they interesting. I'm going to talk about chaos, which is the only thing to mention in the talk, because chaos in the world of mathematics and physics has a very specific meaning, and it's related to triples in a very interesting way. And then finally, I'm going to talk about unstable or stability in general and what it means in the context of triples. But before we go to this very interesting topic, we're going to start a bit closer to home with the star, with our sun, which, just like all the other twinkling lights in the sky, is a star. And even though we love our sun dearly when it does decide to show up, I'm here to say that the sun is not particularly special. And the reason that I say this is that when we look at the billions and billions of stars around us, and we compare them to our own sun, then we find that the sun is actually very average in certain things. So it's a very average, it has a very average mass, so how much it weighs. It has a very average size, and it has a very average temperature. However, there's one property that the sun has that is actually a little bit off the average, and that is its solidity, the fact that it is alone. Because it turns out that most of the stars that we see have at least one companion star. So what does this mean? Well, it means that just like the moon goes around the Earth, a star can have another star going around itself. When you have two stars that are going around each other, orbiting each other, we call this a binary star. So an example of this is shown in this computer animation where you see two stars going around each other. So if you don't believe me, we actually have also images of this. So this is a series of images of the star system, which shows the star Alpha B that is going around its companion star, Alpha A. Now, I could talk for hours about binaries and how interesting they are, because there's so many cool things that can happen when you have two stars. But in this talk, I'm going to be focusing on how they move, or how they move around each other, so the orbits. So what I'll show here are a few computer simulations of different types of binaries. So the way the orbits of binaries can depend on different things, such as how heavy the stars are and how far apart they are. So here you'll see a few systems with varying properties. So I don't know what to say when I ask. Can anyone see what is, for example, different in this column of systems? Like, what am I changing in the system? There's only two things that are changing. One thing I'm changing in this direction, and one thing I'm changing in this direction. Nope. Yes, mass, exactly. Oops. So, in this case, the star is much heavier, so it moves, it feels same gravity, but gets less acceleration because it's more massive. Here they are the same mass, we're moving in exactly the same orbits. And here, in this direction, we're changing the eccentricity, as was mentioned in the quiz, to how oval essentially this orbit is. So one thing I want to mention about binaries is that if we assume, which is actually not true, but let's assume that the stars don't change at all, then these two stars will continue to orbit each other in the same orbit, essentially indefinitely. So we say that they are stable. So I mentioned that we have an analytical solution for them, so we can predict the position of those at any time in the future, assuming that nothing happens to the stars. Okay, so now that we know a bit about binaries, what happens if we add a third star? Because like I mentioned, most stars have at least one companion, which of course means that you can have some stars that have 2 or 3 or more companions. So that leads us to the topic of triple stars, which is when you have one star with 2 companions, so a system with 3 stars in total. So again, or actually, if you don't believe me again, the closest star system, which was spoiled in the quiz, Proxima Centauri is the closest star to us. And when I say closest, I mean it's about 25 trillion kilometers away, which is really close. And the Proxima Centauri is actually orbiting a binary system. So here you have two stars, Alpha Centauri B and Alpha Centauri A, that are going around each other, and then much further away, you have the star Proxima Centauri, which is itself going around binary. So what this is, actually, all the triples that we observe have this kind of configuration, where you have one binary with two stars, and then you have the third star that is going around the binary itself in a wide orbit. This is what we call a hierarchical. So again, I'll show some computer simulations of this, and what you'll see is that this actually looks quite similar to the binary bodies that we saw before, except that now instead of two bodies we have three, and the orbits look similar, but the other body is now itself a binary. So you can see here you see the two stars approaching each other. And they again are orbiting the third star. And what you see in this direction is that the distance between these two stars in the inner body is getting bigger. And here you can see it in this direction, actually the eccentricity increases. But the most important is that you see the distance here is larger. The reason I mention this is that with the triple star system, they are no longer, by definition, stable. That means that even if the stars don't change, the system can actually disintegrate. It doesn't necessarily remain in this exact orbital configuration indefinitely. And what determines whether or not it is stable, how stable it is how small is this distance between these two stars versus this one. So this system, which has very small distance here and quite a large distance here, is very stable. And this system here, which has quite a big distance, and this is the same, but of course it's not bigger, is less stable. So, actually, I was only showing you a portion of this script. So now, if we look at the systems here, where this distance is even bigger, and the eccentricity is higher, you can see that you no longer have this hierarchical triplet. And this is very unstable. So we can look at one of these in a bit more detail, because what does it actually mean to be unstable? Well, as we'll see in this example, see that the orbits are changing very quickly. Every time they pass, something is changing, and even you'll see in detail that like the pairs are changing. Now it's blue, and now it's blue and yellow together. Now it's blue, like green and yellow. So all sorts of crazy things are happening here. And you cannot say that the system is hierarchical because it doesn't have this stableness or the outer star and the inner bodies. Okay, but so what? So why is this interesting? Well, it turns out that once a triple system is unstable, it actually gets destroyed quite quickly. And what we mean by destroyed is that there are two main scenarios that can happen. One of them is that during these chaotic interaction, like things are changing and crazy stuff is happening, at some point, one of the stars can get so close to the other two that it gets a very high speed, and it just gets kicked out in the system, like you see here, like you just saw here. So I'll call it as I was talking. You can see again that every time they pass, orbits are changing slightly. Essentially, they get eventually get closer and eventually they get so close that they eject, and they are never to see each other, unfortunately. So this is what we call an ejection. The other scenario is what we have is that at some point, two of the stars can get so close that they actually touch, and we say that they collide, which means that they basically become one bigger star. They collide and they merge into bigger stars. The actual truth is that we don't exactly know what happens when two stars collide. Let's say that they merge together in a bigger star. It's harder to see here because the stars are very small, so you have to take my word for it. At some point, they get so close that they touch. So, okay. Then I've talked about stability and what can happen when a triple is not stable. So let's go to the third topic, which is chaos. So So, like I mentioned, chaos in mathematics and physics means something very specific. It means sensitivity to initial conditions. Okay, so what does that mean? Well, it means that if you have something that moves, then if you want to, for example, do a cube simulation of how this moves, for example, you want to do a cube simulation to start in orbit, then if it's sensitive to the initial condition, that means that if you change the position that the star has a little bit, the final path that the body takes is going to change a lot. So it's sensitive to your star. So a classic example of this is the double pendulum. So here you see a simulation, actually I'm going to talk about it. So here you have two simulations of a double pendulum. So that is a pendulum that's hanging and then attached to the pendulum is another pendulum. And what you'll see is that it looks like there's one simulation there, but it's actually two. But one of them is started slightly in a different place than the other one. And you'll see that at the beginning you don't see a difference, but actually very quickly they become separate and they start taking completely different paths. And this, they take very different paths, even though they started very similar places. So this is chaos. And it turns out that triples that are not stable are very chaotic. And to show this, I'm showing here a series of simulations of triples that are put on top of each other into one movie. This is a triple that is unstable, but they're all the same system. In every single simulation, the stars have the same mass, there's the same center interactions, as it's called. Distance between the stars is the same, eccentricity is the same. The only thing that's different between these simulations is where in the orbit I start. And what you see very quickly is that they completely separate into different systems. And this can, of course, affect the final outcome, whether you eject one of the stars or whether you cause a collision. So I'm just going to let this play because it's really cool. So these are not this many bodies in one simulation. They're independent simulations that are quickly coupled. So in each one there is one triple system. And if this was a very stable triple system, these would actually completely overlap. You wouldn't see any difference. But because it's so unstable and chaotic, slightly different changes to where you start leads to this very different and I have to say really. And actually, on that bombshell, it's time to end. And yeah, thank you. You mean triples, how triples form?
Yeah, well, is there a simulation with basically infinite amount of starting conditions? But do we know any restrictions that are imposed by the information process?
We know very little about how triples are formed, actually, but the one condition we can set is that it has to be stable, because like I mentioned, if a triple is unstable, it will actually get destroyed very quickly. So it won't really be a triple for a long time. So our restriction is, but on birth, it has to be stable, and we have mathematical equations to check whether the triple is stable. So that's under the main restriction.
If you can observe it, then it will stable for information.
Yeah, and it's still
it might
stable.
not form stably, but we have no idea.
No. If it didn't form stable, it would probably disintegrate quickly, but like I said, we know very little about this.
When the ejection event happened, what have you observed that happened before?
We haven't observed it happen. As far as I know, we have a few candidates stars that we think are the result of this kind of thing happening. And the way that we can look at this is that when you have a triple ejection, you of course have the binary of the two remaining stars will also get ejected in the opposite direction. So if you find a star that is moving in a certain direction with quite a high speed, and you look and you see, is there a binary that is moving at exactly the opposite angle, that's a good candidate. As far as I know, I'm not an observer, but as far as I know, we don't have a candidate for this, I think, maybe. It's very hard to come.
Okay, you can predict individually the path of the body in the system, but can you, as a system as a whole, predict the time it will take to reach to a point of an ejection or a collapse? You can know which of the bodies, but as a system.
Yeah, that's a very good question. So what most people use is that we have this criteria where it tells you is the system stable or not. If it's not, we assume that it's going to actually disintegrate very quickly. But simulations have found that it isn't necessarily that fast. So people have developed other mathematical methods that instead of giving you like yes, no, it's stable, it gives you how long until it's likely that it disintegrates, gets destroyed. So yes, there are methods for doing that. It's a bunch of them.
Follow-up question, what is very fast? What time scales are we talking about?
Yeah, good question. So when I say very fast, I of course mean tens to hundreds of thousands of years, which of course is super fast in astronomy. But essentially what we mean is like, it takes just a few periods to start around. When we talk of long periods, we talk maybe hundreds of thousands of millions of orbits, but short is maybe like tens of hundreds. So it's related to the orbit period. I don't know who's first. I think in the back all the way, yeah. Yeah, so there's that what I mentioned before, we're looking at like the velocity if they're ejected, but you can also have triples where you have a collision, right, as I mentioned, and then you're left with a binary system because two of the stars become one and you have another one, so you're left with two star binary system. And two stars that collide or merge into one, we expect them to have quite weird properties that looks different from the normal star. So there are some stars that we've seen are like, it looks a bit different than what we expect. Could have been a triple where two of the stars collided and merged. The sun was likely always yes. I think so. Yeah.
As stars evolve, you have gas loss.
Yeah.
Have you done simulations of what that would mean to the stability of the triple system?
Yes, exactly. So, like I said, triples are unstable. The distance between the two inner ones is quite large compared to the outer. When stars live their lives, especially the most heavy stars, they lose a lot of their gas. They're sending it out in stellar winds, and this actually widens the orbit. It actually increases the distance. So stars that are stable can actually become unstable because of exactly what you said. Losing mass, and that's widening the orbit, and then it can become unstable because it becomes widening. So that's actually what we're looking for. So we've done simulations.
Is it actually likely that at some point they will dissociate because of this?
We have some estimates, like we think around 2% of triples become unstable because of this mechanism, but there are also other mechanisms that can cause them to become unstable. So that's very good.
I have two questions. One is that actually a follow-up to that one. Do you account for, let's say, mass loss in accretion due to one star being too big and one being too small, and then when they come too close, maybe there's some mass transfer between the stars. Then how do the dynamics change?
Yes, that's an excellent question. So that's actually the other mechanism that I just talked about. That is when you have stars that are close enough that you start transferring gas onto the other stars. Under certain conditions, this can also cause the orbit to widen. There are reasons for, we haven't really studied this very well, and there are a few reasons. It's very hard to model how much transfer between stars, especially if the orbit is eccentric and not circular. In triples, the inner orbit tends to be eccentric. So this has not been studied very well, and hopefully in the future, it's actually something we'll do.
And the second one is, how far are we away from maybe simulating merging planetary systems, I mean solar systems, together, and how that affects maybe? Because there might be heavy exoplanets around these stars which might also influence.
I mean, you could pretty easily simulate merging solar systems. That's just a few bodies, but I don't know if someone can, but it should be pretty easy. And people can do millions of bodies together, and it's a few star systems can have 20. So, but it should be feasible.
I have a question regarding more stars. Extrapolating from the presentation and thinking that we have a lot of stars, I'm thinking that the likelihood is that the system is going towards a chaotic situation. That's my assumption. But then when I'm reading about globular clusters, I'm seeing there's some kind of stability. Globular clusters seem to be some of the oldest objects in the universe. And I was wondering if you can, why are they so stable? Globular clusters, why don't we have chaotic dynamics in globular clusters?
That's an excellent question. I haven't studied clusters like this. I look at multiples in isolation. What I know is that there is all sorts of chaotic things happening inside a cluster all the time. There are stars coming close to each other, things like this. And they do, but why they stay together, that's not my focus, right?
It's okay.
Okay. Yeah, you can.
Right. So in the event of a collision, would it be a gravity wave to simulate LIGO would be able to detect?
Good question. In the case of two stars, nothing that LIGO could detect. They would merge before they send out powerful enough waves. If you have two black holes, because you can have black holes in these triples, it's actually something we're working on right now, then yes, you can get gravitational waves from them. But in a direct collision, even if we could detect it, they wouldn't really be collisions, so they wouldn't be gravitational waves. So also you see when you get this in spiral and they get closer and closer and move faster and faster. Or with like a direct collision, if we assume that they immediately merge, then I don't think it would send gravitational waves, but I'm also not sure. That's a good question. As far as I know, the highest we've seen is 6 or 7. 7. Okay. Yeah. But I think if you won't have a hierarchical 200,000 system at some point. Yeah. So I think we're talking very different scales. We're talking a few, and then millions up to like what they are very different.
I'm wondering about this, the scale of these hierarchical systems, particularly in the Centauri. So, for instance, if you compare to our solar system, the outside star, how far is it?
Someone correct me if I'm wrong, but I believe the orbit is about 10,000 AU. So AU, for those who don't know, is the distance from the Earth to the Sun. So it's 10,000 times more than we are to the
So it's
thousand.
really far out.
Very hierarchical, very stable, not like the books at all.